In the mid 1800s, we started to realize that you couldn't just define compounds by their molecular formula. Arrangement of atoms made a difference. So, if you remember back to a couple of slides ago, I mentioned that the molecular formula of dimethyl ether wasn't sufficient to give you information, enough information about the arrangement of those atoms. And the reason I said that is because dimethyl ether's molecular formula was C2H6O. But dimethyl ether isn't the only chemical that can have that molecular formula. So here's dimethyl ether, right? C2H6O. And here's ethanol. Ethanol also has the molecular formula C2, 1, 2, H6, 1, 2, 3, 4, 5, 6, O. So dimethyl ether and ethanol have the same chemical formula, but you can see that they're laid out differently. This oxygen in dimethyl ether is bonded to 2 carbons. This oxygen in ethanol is bonded to 1 carbon and a hydrogen. That's a difference. The carbons in ethanol are bonded to each other. The carbons in dimethyl ether are not bonded to each other. That's a difference. Here's the carbon in ethanol with only 2 bonds to hydrogen. In dimethyl ether, both carbons have 3 bonds to hydrogen. That's different. These are different chemical structures. And because they have a different bonding arrangement of their atoms, they have different properties too. Look at the boiling points, for example. Dimethyl ether has a boiling point of minus 23C. That's cold, right? That's give or take 0, right? A little bit below 0 Fahrenheit, right? So that's really, really chilly, right? That boils on the coldest Rochester winter day, right? Ethanol, however, has a boiling point of 78 degrees, right? And that's pretty warm, right? Water is 100, right? Room temperature is 37. So, halfway between, or not room temperature, body temperature is 37. So halfway between body temperature and water, right? You're not even able to boil ethanol. So it really takes some heat to boil ethanol. And that's very different than dimethyl ether. Dimethyl ether will boil on the coldest Rochester day. So these are compounds with the same chemical formula, but different structural arrangements. And we call these isomers. And specifically, if you remember back to general chemistry, we call these constitutional isomers. Constitutional because they have the same constituents, right? The same chemical formulas, same constituents, but different formulas. Therefore, they're isomers, right? So we're going to see the word isomers pop up over and over again. Same chemical formula, same constituents, but different arrangements. So constitutional isomers describes that situation. We're going to see the term isomers pop up over and over again. And I believe chapter 3 or maybe 4. I think chapter 4 we're going to spend a ton of time talking about isomers. So stay tuned for that. Okay, so we've already mentioned this a little bit before, but we're now going to talk about some bonding patterns. Now, we've seen this with carbon specifically, but with all of those second row elements, we have very specific bonding patterns that we're going to see over and over and over again. So with carbon, we're going to call carbon tetravalent because it always makes 4 bonds. And remember, that was the basis of being able to draw carbons as ends and bends, right, and not drawing in the hydrogens. Because we know carbon always has 4 bonds. Therefore, anything that's missing, right, is going to be a hydrogen, and it's an implicit hydrogen. But we can do the same analysis with nitrogen. Because nitrogen's Lewis structure of the atom, right, you can see it has 5 valence electrons. It only needs to make 3 bonds in order to get to a complete octet. Therefore, nitrogen will generally have 3 bonds. And if you see nitrogen with more or less than 3 bonds, it needs to have a charge because something is different. Oxygen, remember oxygen has a Lewis structure. Hold on, let me draw this a little bit better. Oxygen's Lewis structure shows its 6 valence electrons, meaning it only needs to pair up 2 of them and only needs to make 2 bonds in order to get to a complete octet. And halogens and hydrogen only need to make 1 bond. Hydrogen, because it needs 1 electron to complete its number 1 shell octet. And halogens, X represents fluorine, chlorine, bromine, and iodine, because they have 7 valence electrons, and they need to make 1 shared pair of electron to get to a complete octet. These bonding patterns hold true typically throughout organic chemistry. We'll see a few examples where they're different. I will point those out when we get to them. Okay, we're going to jump now into a little bit about atomic orbitals. And don't freak out about this. Atomic orbitals, they look scary. We're going to take a pretty qualitative approach to atomic orbitals in organic chemistry here. So don't worry too bad if you're looking at atomic orbitals and you're like, what the heck is this, right? Don't worry too bad. We're going to take a pretty qualitative approach here. All right. So quantum mechanics is really the sort of origin of atomic orbitals. And quantum mechanics was really established in the 20s. There's a few famous scientists you might recognize. Probably the one that you're going to know the most is Albert Einstein. Was pretty pivotal in this. And quantum mechanics discovered that electrons had wave properties. And if you remember back to general chemistry, you might remember somebody saying something about wave-particle duality when it comes to electrons. Right? Electrons have properties of both waves and particles. And this is what we're tapping into right now. So because electrons have wave properties, it turns out that you can find a mathematical solution for the shapes of the orbitals of electrons around a nucleus. And the mathematical solution is done with a wave function, and that is beyond our scope here as organic chemists. Go take physical chemistry. Go take physical chemistry, and you'll get to do that. I'm an organic chemist. I can't do that. It's been so many years since I did that as a student that I don't remember how, and I don't like to do that. That's a lot of math. So what we do, though, is we take a look at those solutions to the wave property of an electron, and we use those to sort of guide our analysis of what an atom looks like in terms of the electronic picture around the atom. So for the S shells, right, the S shells are really, really simple. The S orbitals look like spheres, right, and that's all that it is. So this represents, right, this sphere represents a 90% probability of finding an electron in that region around the nucleus. So for the S orbitals, it just looks like a sphere, and at any given time, there's a 90% chance that you're going to find an electron in that sphere around the nucleus, right? And that percentage chance gets smaller as you go outside of that sphere. For the 2s, right, it's the same thing, right? For the 2s, there's a bigger sphere that's sort of around the 1s, right? So in the 1s orbital, it's nice and small, tight around the nucleus, 2 electrons. For the 2s orbital, it's a bigger sphere that's around the nucleus, around the 1s orbital as well. And that's what we're showing in these pictures down here. Okay, so this is just what I was saying on the last slide, right? An orbital is a region where there's a 90% probability of finding an electron. All right, so if you think about a wave, right? Electrons are like a wave, and electrons can have sort of a region where they're positive and a region where they're negative, just like a wave. So if you think of a wave moving on a lake, there are points along that wave where it's above the average surface of the lake, and there are points where it's below the average surface of the lake. And we would call those the positive and the negative phase of the wave. And electrons have a similar phase, right? They can be sort of above the node in this case, or below the node, right? And we're going to call that the phase of the electron. Now, electrons' wave function phases can be plus, minus, or zero, right? That doesn't indicate charge. We're not talking about charge. Electrons are negatively charged. They always have negative charges because, by nature of them, by definition of them being an electron. But in terms of their wave functions, they can be in a positive phase or a negative phase. So there is some really interesting predictive work we can do with that, and this matches experimental data quite nicely. So we like to use this as sort of our theory behind atomic orbitals. And what that means is, when you get to more complicated orbitals, more than just the sphere-shaped orbitals, you have orbitals with multiple phases. So once you get to the p orbitals, so we had the 1s orbital and the 2s orbital, and going through the 1s and the 2s orbital, those were just spheres, right? They had nodes at the center, right? But in general, the entire orbital was in the same phase. Once you get to the p orbital, they have a different shape to them. The p orbitals typically have two lobes, right? And one is a positive phased lobe and one is a negative phased lobe. And you can think about this like the wave, where the positive is where the wave is above the surface of the lake, and the negative is where the wave is below the surface of the lake. And in this case, because it's a circular wave, right, it looks like this structure here, right, where we have a node in the middle and a lobe above the node where the phase is one direction positive, and a lobe below the node where the phase is one direction negative. So node, by the way, just means an area where there is no electron density. And in this case, the nucleus of the atom is the node. So the p orbital is generally aligned in such a way that the one phase is above the nucleus and one phase is below, or one lobe of the p orbital is above and one lobe is below. Now, these p orbitals are going to be very important when it comes to making pi bonds, and or double bonds, I should say. And we're going to talk about that. That's going to be very important when it comes to doing some chemistry. So we're going to talk about that a bit more further down the line. All right, so if you remember when we drew all of those electron configurations, right, starting with the 1s, going to the 2s, 2s, and then when we got to the 2p, you saw me do this earlier in this chapter. I drew three different lines, and those three different lines represented the three different orientations of the 2p orbitals. So there are three different orientations, just like there are three dimensions in space, right? The three orientations of the 2p orbitals are going to correspond to those three dimensions in space, x, y, and z. So you can see the 2py orbital is the one where the orbital is aligned up on the y-axis. The 2px orbital is where it's aligned on the x-axis, and the 2pz is where it's aligned on the z-axis. All right. Here's a word that you might not have seen before, degenerate. In terms of orbitals, this word specifically means that these orbitals have the same energy. So even though they're aligned differently, these orbitals have the same energy because they're the same shape, the same size, and the same distance away from the nucleus, right? So each one of these, right, has a node in the middle at the intersection of all the axes. And that intersection is the nucleus of the atom. So if you have an atom with a full number 2 shell, let's say neon, for example, you're going to have all three of those p orbitals aligned over top of each other. You're going to have your nucleus, you're going to have your 1s orbital, you're going to have your 2s orbital, and forgive my crappy orbital pictures, I'm really bad at this. And then you're going to have your 2py, your 2px, and your 2pz. all lined up over a single nucleus, right? And so we're building these orbitals successively on top of each other. And electrons populate whichever one they happen to be in at a given time. So all three of those orbitals are around the nucleus at the same time if you have electrons to fill them all. All right, so here is a little practice, right? And the question is, complete the following electron configurations. The way you go about doing something like this is you go look at the periodic table and you say, here's boron. Boron has 3 valence electrons. It's 3 electrons in its valence shell, which happens to be the number 2 shell, right? The number 2 shell. 3 valence electrons. So 1s shell is filled. In the 2 shell, there should be 3, like that. Carbon has 4, so 1s shell is filled. In the 2 shell, there should be 4. And now I have degenerate orbitals. I'm circling the degenerate orbitals here. And in the nitrogen, nitrogen has 5 valence electrons. So 1s is filled. 1, 2, 3, 4, 5. All 3 of these orbitals are degenerate. And in oxygen, I have 6 valence electrons. So 1, 2 in the 1s. 1, 2, 3, 4, 5, 6. So now only these 2 are degenerate.